Hey everyone, it's Sol. I know it has been quite some time, to say the least, since I've posted my last video, but that's just because I've been caught up in all this college application mess along with school. So, but I am done with all of that now, and since the AMC is coming up relatively soon, I thought I will try to post some videos about problem-solving strategies that will hopefully help you on the AMC 10, 12, and possibly the AME. So, as you can tell from the title of this video, we're going to be going over a 3D geometry problem-solving strategy. Mainly, and as you can also tell from the title, mainly this idea of cross-sectional area and evaluating a 2D figure that you can get from a 3D figure. Alright, so this problem is from the 2014 AMC 12B, I believe. And this is problem 19, which means it's a pretty difficult problem on the AMC. So, if we look at the problem, it says that a sphere is inscribed in a truncated right circular cone, and the volume of the truncated cone is twice that of the sphere. What is the ratio of the radius of the bottom base of the truncated cone to the radius of the top base of the truncated cone? Okay, before we worry about this cross-sectional thing that I was going to talk about, perhaps we should first go over this volume condition that they so nicely gave us in the first place. The volume of the truncated cone is twice that of the sphere. Okay, so I've labeled the height of the truncated cone as 2h, just because I thought it'd be convenient, because then we can express the radius of the sphere as just h. So, well, we have the volume of the sphere of, well, twice the volume of the sphere would be, well, let me make sure this is working, 2 times 4/3 pi h cubed, because that is the radius of the sphere. And, oh, okay, the volume of a truncated cone. That is a little more obscure. It's not as commonly known, but if you guys would like to derive it, I will drop a hint, though not go into detail. Basically, what you can think of is you can use the properties of similar triangles to find the radius, or to find the height of this cone, the cone that was cut off, and then subtract the area of this, or the volume of this cone from the volume of the total cone. So that's the idea behind the formula, but I will just give it to you guys for the sake of it. It's going to be pi over 3, as we expect, because it's kind of a factor shared amongst all cones, times the height of the truncated cone, which is 2h in this case, times r squared plus big R, little r, plus r squared. Okay, so already from this, there are quite a few terms that cancel out. We have a term here, we have pi's over 3's, we have an h that cancels out, so this becomes a squared, and we have a 2 that cancels out. So if we write everything else down, then we get 4h squared is equal to r squared plus big R, little r plus little r squared. Cool. So now we have some relationship between the height of the sphere and the radii of the truncated cone. So now let's get into this idea of cross-sectional area. So what do I mean by cross-sectional area? Well, the cross-section of, say, like an egg, I don't know, would just be like the yolk of it, or the egg white and the egg yolk of it, right? This is the cross-sectional area of an egg, per se. So we kind of want to do something similar, although a weird example, we kind of want to do something similar with this shape, because I think it'll simplify it a lot. Taking the cross-sectional area of a volume, of a 3-dimensional figure, will give us a 2-dimensional one. So basically, to get the shape of the egg that we had to cut the egg in half, right? We had to cut it like this, and then we have like maybe a knife here, right? And then we just bring the knife down on the egg. And so we kind of want to do something similar. Oh man, that was so weird. We kind of want to do something similar with this. this figure right here. We want to take a knife and cut it down the center of this truncated cone so that we can see what shapes are made. And so if we imagine it, the cross-section of a truncated cone would probably be a trapezoid, since the cross-sectional area of just a cone is a triangle, and we just basically cut off the top, which is another triangle, which makes a trapezoid. And of course, the cross-sectional area of a sphere is a circle. So we have a circle inscribed in this trapezoid, trying to make this decent looking. Okay, that looks fine. So since this circle is inscribed in this trapezoid, we have a lot of things to work with, right? The great thing about this strategy is that we converted a 3D problem into a 2D problem, which is much easier to work with, especially with all these tangent points here, 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 and here. So let's just go ahead and draw lines from the center to these tangent points. So we have the diameter right here, 2h, and then we have this length right here, and this length right here. Okay, so one nice property about tangents is that they're of equal length when they meet. So since this length is r, and this length is also r, although this length is also r, well, that means this length must be r because it is a tangent that meets this other tangent. And we can say the same for big R. We can label this as big R and big R. Cool. So we know that this height is, of course, 2h, like I said. And you can see the resemblance between, the 2D figure that we came up with and the 3D figure that was given. So the next thing I want to do is find the relationship, right? We want to find some sort of relationship between r squared, or between r, big R, little r, and h. So I think what we can do is just use some classic Pythagorean theorem. If we just drop an altitude right here, this must have the same length of 2h, and well, the hypotenuse of this triangle would have our length big R plus r, and this leg right here, well, if we just transpose this length must be r, little r, and since this total length must be big R, this leg right here must be big R minus little r. And now we can just set up our Pythagorean theorem equation from this. We have 2h squared plus the other leg, r minus r squared, is equal to big R plus little r squared. And I'm already liking the looks of this equation because it can just be simplified by so much. So we have 4h squared plus r squared, big R squared minus 2 big R little r plus little r squared is equal to big R squared plus 2 big R little r plus r squared. So a lot of things cancel out. The ugly r squared terms cancel out, and we get this nice relation that 4h squared is equal to, well, 4 big R little r, and I did this just by adding 2 big R little r to both sides and combining the like terms. And if you recall, we actually had a relation between 4h squared and big R and little r. We had that big R squared plus big R times little r plus little r squared is equal to 4h squared. Hey, we found another expression for 4h squared. Let's just go and plug it in. And then we can kind of get rid of this h term, so we only have to worry about r, big R and little r, which was the objective in the first place. So let me clean up the board and then we'll get to the final equation to try and solve it. Alright, so to pick up where we left off, we had this equation after making this substitution that 4h squared was the same thing as 4 big R times little r. So let's just try to move this over here so that it becomes r squared minus 3 big R little r plus r squared is 0. Okay, and keep in mind from this, from the condition of the, or from what the problem is asking for, it asks for the ratio of the bottom base, big R, to the radius of the top base, little r. Okay, so how can we find this, especially when we have an equation like this? Well, this is a pretty common trick when solving for ratios like this. We can divide everything by r squared, little r squared. And what will this do? Well, this will give us the equation big R over little r squared minus 3 big R over little r plus 1 equals 0. And we can, and this is just a normal quadratic equation that you've probably been solving since maybe middle school, right? So from this, from there it's pretty simple. We can, if it makes you a bit more comfortable, we can actually substitute big R over little r with something like a, so it becomes the same thing as solving a squared minus 3a plus 1 equals 0. And from here we can just use the quadratic formula to find the ratio that we sought for so long. So let's just do this real quick. So it'd be negative b, or negative 3, which is positive 3, plus or minus the square root of b squared, which is negative 3 squared, or 9, minus 4a, which is 1, c, which is also 1, all over 2a, which is just 2. So this becomes 3 plus or minus the square root of 5 over 2. And, well, the only one that looks remotely like this is e. Now, before I end this video here, I would like to explain why this 3 minus root 5 over 2 does not make sense. Well, intuitively, big R over little r should be greater than 1 because big R is, well, greater than little r, it looks like. And so, if we kind of actually evaluate 3 minus root 5 over 2, we'll find that that is actually less than 1, which implies that little r is bigger than big R, which is just not true. So that is why we take the plus, version of this, and we have our answer as E, and we are done.